Hi students, today let's have a look at the physical properties of waves. Physical properties are things like velocity of the wave, the energy stored in the wave, the pressure difference created as the wave travels, all these properties. So let's begin. So what is the velocity of a wave on a string? We've already studied that a wave on a string is a transverse wave. And the most popular transverse wave that we use is the one we create in a string. So what will be the wave velocity in this case? As you can see, this is the wave that is created on a string. We already know that the formula for velocity is velocity equal to frequency into wavelength. But if we want to calculate the velocity in terms of the properties of the string, then the velocity of a transverse wave on a string will be V equal to root of T by mu. Now what is T? T is the tension in the string. In the chapter force we studied, remember, that a string has a certain value of tension in it. What is mu? Mu is the mass per unit length of the string. So if the length of this string is 1 meter and its mass is say 2 kg, then its mass per unit length is 2 kg per meter. But where does this formula come from? V equal to root T divided by mu. Can we derive this ourselves? Let's try. So let's calculate the velocity of a transverse wave in a string. But we'll do it in a slightly weird way. We'll calculate the velocity of a transverse wave in a string from the frame of reference of a man who is moving at the same velocity as the wave. So have a look at this man here. I know he looks a bit crazy, but let's be friends with him for now. So we will calculate the velocity of the transverse wave from this man's frame of reference. And this man will be moving at a velocity v same as the velocity of the wave. Here, you can have a look at him again. So we will perform all our calculations for the velocity of the transverse wave from this man's frame of reference. Why will we do that? Doing that will help us a lot in simplifying the variables involved. I'll come to that later, but for now let's use this frame of reference. Now, if this man were at rest, he would actually see the wave moving. In fact, anyone at rest would see the wave moving with a velocity v. For anyone at rest, the string, however, would be at rest. For example, if you were looking at the string, you would see the string going up and down, and you would see the movement of the wave towards the right. But you would not see the movement of the string towards the right, because as we all know, in a transverse wave, the particles just move up and down. So the string particles would just be moving up and down as the wave moved from left to right. But things are different in this man's frame of reference. In this man's frame of reference, the wave is at rest. That is because he is moving with the same velocity as the wave. And similarly, in this man's frame of reference, the string is not at rest. The string is moving to the left with a velocity v. That is because the man is moving to the right with a velocity v. So in his frame of reference, the string, even though it is actually not moving to the right or left or anywhere, in his frame of reference, the string will be seen moving to the left with a velocity v. Understood? I know this might sound a bit complicated initially, but think about it and you'll understand. And I'll repeat anyway. In this man's frame of reference, the string will be moving to the left with a velocity v, and the wave will be at rest. So this man will not even see the wave moving. He'll simply see the string moving like this towards the left. Now let's have a closer look at the string. Here, let's take a portion of the string. This portion. What are the forces acting on this portion of the string? Let's write the equation of motion of this portion of the string. That will help us find the velocity of the string in terms of the properties of the string. Let's magnify this portion. Here it is. That small portion has now been magnified. This small portion we've taken is so small that you can call it an element of the string. It's an infinitesimally small portion of the string. Here it is. What are the forces acting on this small string element? There's of course tension from the other parts of the string, and the velocity of this element is v towards the left. Why is the velocity v? Because as I said, we're performing all our calculations from the frame of a man who is moving at a velocity v to the right along with the wave. This man will see the string moving towards the left with a velocity v. That's the reason that the velocity of the element is v towards the left. Let the length of this element be delta L. Delta L is a very small quantity because we've just considered a very infinitesimally small portion of the string. Now let's assume that this small string element here is moving on a circular path. If that is so, a centripetal force equal to delta m into v square by r will act towards the center of this circle, where delta m is the mass of the string element. This is because we know that if a body of mass m is travelling on a circular path, then a force equal to mv square by r is exerted towards the center of the circular motion. We can equate delta m into v square by r, the centripetal force because of the motion of the string, to the net downward tension force acting on the string element. When we do that, we can get the value of the string's velocity. Let's see how we'll proceed. As you can see, we have assumed this angle here between the line joining the center of the circle and the center of the element and the normal at the end of the element to be theta. The angle here will also be theta because these two angles are alternate angles. Thus, we can conclude that the net downward tension force acting on the string element will be 2t sine theta, right here. Now, the string element delta L is so small that we can almost assume it to be a straight line. I know, I had just said that the string element was travelling in a circular path, and now I am asking you to assume it to be a straight line. But then these assumptions do hold true when the length of the element is very small, or as I had said earlier, infinitesimally small. So well, if we do assume this small string element to be a straight line, we can then say that sine theta is delta L by 2 divided by r, opposite side divided by the radius. Then we can substitute this value of sine theta in the expression 2t sine theta. That is, 2t sine theta is equal to t into delta L divided by r. Now we can equate 2t sine theta by the centripetal force delta m into v square by r. So we see that t delta L by r is equal to delta m into v square by r. Now when we take delta L here to the other side, it comes in the denominator, and delta m divided by delta L is mu, that is the mass per unit length. That gives us the final expression. V is equal to under root of t divided by mu, or the velocity of movement of a transverse wave in a string is equal to square root of tension divided by mass per unit length. There, we've derived the expression. As you might have observed in this derivation, we've made a lot of assumptions. We first considered the element to be a circle, then we said it was a straight line. All these assumptions are simplifications of a very complex derivation, but this will suffice for now. And now, after all this theory, it's time to solve some IIT problems. Here, take a look. A mass of 2 kg is hanging from a string of mass 6 kg. The length of the string is 12 meters. Suddenly, a pulse with wavelength equal to 0.06 meters is generated here at the bottom.